Uh, right when I'm recording, this is great. What is the question? Borrowing a calculator. Awesome. That is Ryan Stevens, unprepared, now on YouTube for all of eternity. We're off to a good start. Okay, so we're going to be taking a little bit of a break in terms of our two triangles in calculating moles and entities, or mass and moles using the molar mass. We are going to still need our ability to calculate a molar mass using our periodic table. All right, so you'll need that out in order to do your calculations. So what we're kind of doing here in this lesson is we're kind of taking a step back historically to think about the way chemists originally thought of chemical compounds. Because the idea of atoms wasn't originated until the early 1800s with Dalton's atomic theory. So before Dalton, and a lot of good chemistry was done in the 1700s. Compounds had names, and elements had names, but there was no knowledge of atoms, and therefore no knowledge of chemical formulas. So if a chemist wanted to identify a substance, the chemical formula, well, it didn't exist. So how did they identify it? Well, they identified it as a percentage mass, all right? So in the 1700s, chemists were learning how to decompose chemicals into their elements. And through a decomposition reaction and some simple mathematics, they could determine the percentage of the mass that each element had in that particular compound. And so that's what they called the percentage composition. So I'm going to teach you how we calculate percentage composition. That's essentially what this lesson is about. It's still a useful calculation, but now we can take the percentage composition information and we can figure out what a chemical formula is. All right? Okay, so let's define percentage composition. And you can write that down. Yep. Oh, excellent. Am I going to out the unprepared? No, I won't do that. Yeah, if you need a periodic table, just come up and grab one. So it's the percentage by mass. So again, that's something that can easily be weighed. Even in the 1700s, with the advent of scales, Lavoisier was determining that we had the laws of conservation of matter, so we had to balance things. And again, this was called the law of constant composition. It meant that each chemical had its specific percentage composition. So all water was the same percentage composition. Okay, so essentially there are two ways in which we can calculate percentage composition. One is starting from the chemical formula. So that's kind of like us existing here now and having the knowledge of atoms and having the knowledge of the way we can cross over charges and determine formulas. So starting from our knowledge that we know now, we can work backwards and calculate the percentage composition. So that's number one. That would be the theoretical method based on the theory of atoms. And then there's experimental methods. Maybe a decomposition reaction, or maybe a synthesis reaction. We're going to do a neutralization reaction that produces carbon dioxide, and then we're going to be able to get data from it. So there is also experimental ways of getting the percentage composition. And that's the way chemists in the 1700s would have done it, experimentally. In the end, in our experiment, ideally, you calculate the theoretical method based on its formula. We do an experiment. We get the experimental method, and they should be the same. We should get the same information if the theory is correct. So using chemical formulas. So for any percentage composition calculation, it's really a percentage calculation. It's the same as any percentage calculation that you do. So let's say, oh, I'll pick some random student that doesn't exist. Oh no, I can't help. I was going to pick on Vanessa again, but I wouldn't do that. Let's say, okay, Vanessa, let's say she got 7 out of 10 on the last, no, not good enough, 8 out of 10 on the last whatever quiz. What percentage did she get? What percentage did she get? Yep, 80%, right? So mathematically, what did you do to get that 80? That's an easy, but how would you, let's change it. Let's say she got 76 out of 90. How would you get the percentage? Yep. And then what? One more step. Times 100, right? 76 divided by 90 times 100. I think that's pretty good. I don't know. That's how we get any percentage. We take whatever we want to study, the number of correct answers, over the total, always a total, times 100. It's going to be the same for this. If I want to know the percentage of hydrogen in water, I need to know the mass of the hydrogen in the water divided by the total times 100, and I've got the percentage hydrogen. So I'm not creating a formula for this because we're really just getting a percentage. So first we need the total. Now, I've already told you that this is one we use over and over again, but I want to write out the masses this time just for the purpose of this example. So again, we're going to our periodic table. We're looking for the mass of water. We're looking for the mass of oxygen. We're looking for the mass of hydrogen. And I've got 16, and then 1.0 times 2, and that gets me 18.0 grams per mole. Okay? So if I want to know the percentage hydrogen in water, well, I'm going to find the mass of the hydrogen, 2. I'm going to divide it by the total, 18, and I'm going to multiply it by 100. I'm literally determining the percentage. So I can go to that line. I'm going to write out 1 times 2 divided by 18 times 100. Now, the reason I write out 1 times 2 is because let's say I had a really big complicated chemical, then I can just grab that line out of the molar mass calculation line. And in this case, it's just 1 times 2. It's pretty easy. But if it was something like calcium phosphate, there might be a big calculation there. We could just grab the calculation. I can do the same with the oxygen. 16 times 1 divided by 18. Then I'll take some numbers when you get them in. What are we getting here for the percentage hydrogen? And let's keep 1 decimal at least. Yeah, what do you got? 11.1%. And now some of you are saying, well, could I just take 100 and subtract 11.1? You could, but let's save that as a check that we've done the math right. When you do the 16 over 18 times 100, what are we getting? Yep. 88 point, should round, I think, to an 88.9. 88.9%. And when we add those two up, it gets us 100%, and therefore we've done it correctly. All right? So, from a formula, it's very simple. Determine the molar mass, take each element, divide it by the total, times 100, and you've determined the percentage mass of the elements in water. Pretty straightforward. We'll do one more example of this type of thing, and then we'll talk about the experimental methods. The experimental methods are the same. There will be a mass of the element and somehow a total mass. That's how we do it. It's always the same. Mass of what we're looking for divided by a total mass. All right, so let's do one more. And let's do a chromium 2 phosphate just so that we've got bigger and uglier numbers to work with. So the chromium 2 is going to cross over the 2 to the other side. The phosphate's a 3. That's going to come down to the chromium. So I think we're looking for something like this. Cr with the 3 crossed over, PO4 2. So we've got some big numbers we're dealing with. Again, I'm hoping I hear the rustling of periodic tables. The clacking of calculator keys. And chromium is one I do not use very often. 51.99, 52.0. Again, you don't need brackets with this. Your calculator, you can just push it through. 16 times 8 plus 31 times 2 plus 52 times 3. We don't even need these numbers totaled up. Even though we're going to do a total over here, we can still write for chromium 52 times 3 at the top, right? We can let the calculator do the work. Does somebody have a molar mass there? Yep, what do you got? Supporters, before we get too far, make sure we're checking, because the worst thing about making a video is that nobody tells me that there's a mistake and we get all the way to the bottom of the question and we got to back up the truck and fix everything. So we like that? Okay. So again, percentage chromium equals, now I need the mass of the chromium, and this is where I've made mistakes when I've rushed. Chromium is first on my list, but in the way I calculate molar masses, it's the last set of numbers in my addition. So sometimes when I'm in a hurry, I write down chromium, but I'll grab the wrong set of numbers. So I'm looking for the 52.0 times 3 divided by the total, 346.0 times 100 to make it a percent, and we crash through. You will have a percent phosphorus, a percent oxygen, and in the end, they should add up to 100. Sometimes, if you add them and they get 99.9, it means you've made a little rounding error somewhere. I don't get too picky on that when I'm marking that type of stuff. And I will take numbers as they come. Yeah, what do we got? 45.0? Okay. Anybody else want to share? If not, I'll take them all from Gage. Doesn't matter to me. What do you got? 17? 17? 0.0? 0.3? All right. And oxygen? Yep. 45.1. I'm concerned. Should I be concerned? 80, 90, 107. I'm very concerned. Which one don't we like? Yep. 30, 37. That will make me a little happier. 47.0. Not liking that. It means I got a 0.3 somewhere. The wheels are falling off. We better learn how to use our calculators. 45.1. All right. 45.1. 17.9. Goodness gracious. Good thing I don't attach your names to my videos. All right. How are we doing? Does it add up to 100 yet? 40, 50, 80. Goodness gracious. That's 14. That's a 6. Are we at 100? 100%. All right. Okay. So that's how we get it from a formula. Simply from the molar mass. Nice and easy. Okay? Now a few examples of how to get it experimentally. From experimental data. If you are writing my note from the phone, I'm not going to do example 2. I'm going to do 1, 3, and 4. So you can see here in questions like this, it's just a description of a chemical reaction that's taken place, and there are obviously masses associated with it. This is a reaction that I wouldn't do here at school. Number one, I don't have chlorine gas. It's not a very nice thing. We try to avoid generating it because it really isn't very nice. The odor is very strong, and not that it's, well, in its high concentration it would be toxic. Anyway, so they don't let me have that. But you could imagine that we could take a chunk of sodium metal, weigh it, get its mass, just like that, and then maybe in a glass vessel that's containing the chlorine gas, we could somehow insert that sodium metal into it, and that will react spontaneously without any heat, and it will react very vigorously and produce lots of light, and in the end, some white substance will be covering the inside of the container, and it would be powdered sodium chloride, powdered salt. And we, in the end, could measure that and determine its mass. So we have the mass of the sodium, and then we have the mass of the compound that's formed, that contains the sodium and the chlorine, all right? So if I want to determine a percentage, all right, and I want to say determine the percentage of sodium, all right? Now, we didn't write this down, but we could have wrote it down in the last method as well. We're going to need the mass of the sodium, right? So that's just an M with a little Na that says mass of the sodium. And I need to divide it by the total mass of the compound. So I always divide it by the mass total and then multiply by 100. That's what we did in the last example. The mass of the oxygen divided by the mass total times 100. Or like when we take the test. What you got right divided by the total times 100. It's always the same. Times 100. Well, what's the mass of the sodium that was used in this experiment? Well, it's right there. They're telling us. 3.45 grams. What's the total of the compound that was formed? Well, it's right there, 8.78 grams. Times 100. That'll get us the percentage sodium. Now, there are only two of them. We could subtract from 100 and get the other one, but let's calculate it out. If I then want the percentage of chlorine, then I'm going to need the mass of the chlorine, again, divided by the mass total. Now, some of you already calculated that. That's good. I'm going to get that information from you in a moment. In this case, how do you think I can determine the mass of the chlorine? What am I going to mathematically do, Ryan? Yeah, total minus the mass of the sodium, because there's only two elements in there, so we can easily take a difference there. Now, I don't need to see these steps written out with all of these letters, but because I'm teaching you how to do it, I'm going to write it out with all the letters. But the mass of the chlorine would be the mass total minus the mass of the sodium. That's going to be 8.78 minus the 3.45. And I'll take a number on that if someone could calculate that for me. Yep. 5.33 grams, and that's the mass of the chlorine. Now we can finish off the second part and check it, because we know how much is left. 5.33 grams divided by the total 8.78 grams times 100, and I'm going to squeeze that one off to the right there. Are you telling me numbers? Which one are you telling me? 39.3%. And do you have the other one as well? 60.7%. And that's good. That totals up 100. We're in good shape. Okay? So when it comes to experimental determination, it takes some logic and a little bit of thinking. That was pretty straightforward. All right. So I'm going to jump past this one. It's very similar to it, except it's a decomposition reaction, and I'm going to jump to number 3 here. So number 3 is more like the experiment that we would do if we had access to the other room and we could use the Bunsen burners. I'll let you write it down and think about it a little bit, and then we will analyze it. I do like questions like this. Very often on tests, you'll see a question like this, because it's an application of chemistry in a laboratory setting. But in our lab, it's going to be a little different, and that's what number 4 is going to be about, and that's why I'm making my new video for number 4. I pay Jackson to do that to keep us awake. Keeps us on our toes. All right, this is a wordy question, as you can see. There's not really much of a way to make it shorter. I actually attempted to make it shorter just before you got here by getting rid of a sentence, and you'll notice I forgot to capitalize my D, where it says determine the experimental percentage composition. So this is an experiment that I like to do, but again, because we don't have access to the lab, we won't be. But let me just describe it. We've all, learned about the different lab equipment, and the crucible is essentially a little tiny little cooking device that we use in order to initiate reactions with heat. It's like a little Dutch oven. You can imagine, if you have cooks, you put that big pot, you put the food in it, and you put it in the oven and let it kind of cook away. So a crucible is like that, and so we start with the crucible and lid empty, and we put it on a scale and we weigh it. And then we put in one of the reactants anyway, in this case, copper metal, and we weigh it again so that through subtraction we can determine the mass of the copper. And then in this case we would put a little chunk of sulfur in there as well, and then we would heat the heck out of it and let the reaction take place. In the end, copper 2 sulfide would be formed, and any of the extra sulfur would probably burn away and become sulfur oxide and leave the crucible. So in the end, the crucible contains our product. So we've got a number that allows us to determine the copper, and a number that allows us to determine the total. And from that, we should be able to determine the percentage composition. So again, I'm going to, just like before, I'm going to have a percentage copper, right, which will be the mass of the copper over the mass of the total, mass of the copper over the mass total times 100, and I'm going to have a percentage sulfur, which is the mass of the sulfur over the mass of the total. And now the trick to this is, how do we get all these masses from those numbers? How do I get a mass of copper? And how do I get a mass of sulfur? And how do I get a mass total from the numbers that were given? That's the question. Are you going to tell me something, Maya? Correct. Simply subtract. So if I want the mass of the copper, I take the mass of the copper crucible and lid and subtract the mass of the crucible and lid. So 22.524 minus 21.511, a very nice, accurate device. And I'm going to squeeze that number in there. I didn't give myself enough room. Does anybody have a number for the mass of the copper? Yep. 1.013, 1.013 grams of copper. Okay? Which one do you want to tell me next? They can be calculated in many different ways. What do you have? 0.252. How did you get that? What did you do? With just the copper itself? Or the crucible lid and copper? Yeah, that's right. That's a good way to do it. If this is crucible lid and copper sulfide, 22776, and I take away the crucible lid and copper, the 225242, then I'll be left with the sulfur. That will work. That's a good number. I like that. Total. Has somebody got a mass total? Somebody got a mass total. Dominic, what do you got? 1.2, sorry, I lost the others. 65, and how did you get that one? From the top one. Yeah, that works good. Once you've got the sulfur and the copper, you could add them up. That would work too. There's all kinds of different ways to get these masses. Do we like them? Do we have supporters on the masses? Are people checking them? Jackson? Did you calculate anything? Right. A general thumbs up isn't what we're looking for at this point. No, really, Ryan, did you check those numbers? I don't want to get too far. Do we like them? We're liking them? We don't want another Shamazel like the percentage Shamazel of example 1. No, that was example 2. All right. So now we can put our numbers in. Copper is going to be 1.013 divided by 1.265 times 100 equals percentage sulfur is going to be, I'll write it out as an equation, mass of sulfur over mass total times 100, and that is 0.252 over 1.265 times 100. And I'll take numbers as they come in. Got Ryan, what do you got? Sorry, I missed that. 80.1, 80.1%. And keep going since you 19.9%. It's looking like we're adding up to 100. Things are looking good. Again, check things out. Make sure they're right. Yes, Jackson.
That is 100.
It is 100. Thank you. It's perfectly 100. No calculator? Nice. So you can see there, that's the same calculation we just did as in example 1, except it's got some experimental data in it. Now for my last example. Again, it is wordy, but this is the method that you will use when completing your analysis of the lab that we do on Monday. So essentially, when you go to do your lab on Monday and you go to analyze it, you want to look back at this next question, okay? Good to go? Well, you're the pencil that's still wiggling away. I'm just waiting for you to get to finished writing. All right. Now, I needed an experiment that didn't involve a Bunsen burner and a synthesis reaction like the last one. So I found an example of an experiment where an acid is reacting with a carbonate. And the balanced chemical equation is not important. The only reason the balanced chemical equation is there is for me to illustrate to you where the carbon in the carbonate goes. On the lab, I have a word equation instead of a balanced chemical equation because it's not important in the analysis. But it's not a bad little lab because we have to do a little extra thinking about where the carbon went in order for us to determine its mass. So in this experiment, I only want to determine the percentage carbon in the sodium carbonate. In the experiment, it's going to be sodium bicarbonate, so it's got a slightly different formula, but it doesn't matter. I would have to do some other experimentation to determine the percentage sodium and the percentage oxygen, but I'm just worried about the percentage carbon in this case. So when we react an acid like HCl with a carbonate, it's a double displacement reaction, and we end up with H2CO3, carbonic acid. That's one of the double decomposition products that will decompose or break down into carbon dioxide and water. Okay? So the carbon in the sodium carbonate, well, what product does it end up in? Where does the carbon in the sodium carbonate go once the reaction is complete? Where does it end up? Where does the carbon end up? Yep, Ryan? In the carbon dioxide. So that carbon ends up in the carbon dioxide. Okay? When we do this experiment, we have our total mass of sodium bicarbonate on a scale in a beaker. And then we add some acid, and it bubbles, and the carbon dioxide leaves. So when the scale gets lighter and lighter, the mass that is lost is equal to the carbon dioxide that's left. So we can determine the mass of the carbon dioxide. So in order to get the mass of the carbon, we need to determine how much carbon is in that carbon dioxide. Once we know that, we'll know the mass of the carbon. We know the mass total, 2.48. So I need to know how much carbon is in 1.02 grams of carbon dioxide. All right. Now there's two ways of doing this. I'm going to show you using the mole way. So I need to figure out first how many moles of carbon dioxide there are in 1.02 grams of carbon dioxide. So we need to figure out mass to moles. Okay? What do I need to turn mass to moles? The molar mass. CO2. Somebody have that? Yep. 44. That's one of those that is common. Okay? I need N from the M. I'm going to make it tell me what equation am I using. N is equal to what's the equation for N? Yep. Nope. Definitely not. Yep. Mass over molar mass. .02 grams divided by 44.0 grams per mole. How many moles of carbon dioxide do we have? Yep. Moles of CO2. Now, from this, we can get moles of C. And we've learned how to do this. That's why this is a nice lab. It puts everything in that we've done. If there's 0.0232 moles of CO2, and I just want the moles of carbon, I had to multiply by something in order to determine how many carbons there were. Yeah, what do you think? Multiply by 1, there's only 1 carbon. So moles of carbon is also 0.0232. And if you want to see where that calculation came from, it's 1 C in each CO2. That's the way I wrote it down before. Multiplied by 1. There's only 1 carbon. All right. Excellent. 0.0232 moles of carbon. We're almost there. I want to know the mass of the carbon that's in it. Well, I know moles of carbon. I want to get mass of carbon. How do I turn moles to mass? Molar mass. But this time it's just the molar mass of carbon. Well, there's the moles. What's the equation for mass? What's the equation for mass going to be? Dom, I'm giving you a second chance. There's the triangle. What's the equation for mass going to be? Yep, times moles. Molar mass times moles. N times molar mass, 0.0232 times 12. You got another number, Sean, there? No? Just throwing the pen down? Taking a rest? Gotcha. Do you have a number, Maya? 0.264. Grams of carbon. Do we like it? Supporters? Uh-oh. Sean's raising his hand. What do you got? Or sorry, Ryan was raising his hand. 2.784. .784 grams of C. Did you fix it? Did you find it, Maya? Okay. Okay. Let's think about what we did. Carbon dioxide has carbon and oxygen in it. We broke it into moles of carbon dioxide. We then pulled out the carbons. There's only 1 in each. So once we counted all the carbon dioxides in moles, we pulled out the carbon. Same number. Now we turned that moles back into mass. I now know the mass of carbon. That's MC. All right? Control that, please. All right? Don't let that slide. We now have the mass of carbon. We also know the total mass. We can easily get now the percentage mass for the carbon because we know the mass of the carbon and we know the total mass. That's the last part in getting this. All right. Yep. Sorry, by what? Because that's the molar mass of carbon by itself. Okay? So, right? So we started, it was carbon dioxide. So we used the molar mass of carbon dioxide to get the moles, right? We then did this times by 1, right? Which then made it just carbon by itself. It's as if we said, forget about the O's, okay? And now, because we want to get the mass of just the carbon, I need to use the molar mass of carbon to get that back. So the carbon dioxide turned it into moles of carbon dioxide. This one turned it into moles of carbon, and now we're putting it back into mass of carbon. Okay? Yep?
Be able to do 12 divided by 44 percentage.
Yes, and multiply it by that. You bet. That's a quick way of doing it too. Yep, that would work. It's the same type thing. Okay. Really, we're just determining the percentage composition. That way works great. But I wanted to use this as a kind of a review example as well, because it touched on everything that we've done, you know what I mean? But that works just fine too. So we have all the information we need. Again, we're just getting the percentage C because I know nothing about the O's and about the NAs. There's no way for me to get that data from this experiment. So I just simply need the mass of carbon over the mass total, just like before. So the last step is easy. The mass of carbon, we determined that in part A. You can just pull that number there. The mass total is the total mass of the sodium bicarbonate we started with. That's in the top part of the question. And multiply it by 100. And then you've got it. Yep. You've already done the math for us? Okay. What was that top number? 0.2784 grams, and I don't remember the first number. It's on the previous slide, and I don't have it. What was the mass of the sodium bicarbonate? 2.48 grams times 100. And what did you say it was? Oh, did you get a number, Vanessa? 11.2. Do we like 11.2? 11.2? 11.2%? It's at the beginning of the question. That's how much sodium bicarbonate we started with, right? That's the total mass. There is a way to check it. I hope I made the question up properly. In the end, in the experiment, right, we're going to get you to determine what it is from theoretical values. Let's do that just quickly. 16 times 3, 12, 23 times 2, right? That's the molar mass of sodium carbonate. And then what is the percentage of carbon? Well, it's 12 divided by that total times 100. And hopefully it's 11.2, or I didn't make the question up very well. And ideally, when we do our experiment on Monday, we get numbers that are close. What is that molar mass of the sodium carbonate? Has somebody run that through a calculator yet? Yeah, Ryan, what do you got? Sorry? 106? 106.0 grams per mole. 12 divided by 106. If make sure we're checking so we're not going too far down the road in case we've screwed something up. What do you get? Times it by 100. 11.3? 11.3? Which means I made up my question good enough. Gets us the same thing. And that's ideally what we want to happen in our experiment on Monday. We want the experimental to be fairly close to the theoretical. Okay? All right. I'm going to stop my video, but that is the end of the lesson.